In this video, we're going to learn about the first fundamental theorem of calculus. And so there's a first and a second. The first one is not what we're going to actually end up using most often, but we'll need to see this first for the second fundamental theorem to make sense when we learn why it is the case. So here's what the first fundamental theorem of calculus tells us. It tells us that if I have the derivative with respect to some variable of an integral from a constant to that variable of a function, and the variable here matches the upper limit, then this will just equal f of x. The derivative of the definite integral with the upper limit being that same variable will just be what the inner function is with x substituted in. A quick rationale for that has to do with the fact that, and this isn't a proof, but this is the idea that we would use if we want to continue to prove this. As x increases, we add basically rectangles, infinitesimally small rectangles that are f of x tall. And so the areas are going to be delta x times f of x. And that's going to be the change in this value. I'll call that y. So the change in y over the change in x will be approximately f of x, or dy dx, or this derivative, will equal f of x. So that's a quick proof idea. You don't need to understand this to be able to do the problems. They're super easy problems. But it's worth having some idea as to why things are the way they are, at least. All right, here's the first example. So in here, I notice that the variable doesn't match with the upper limit. This is a constant, but it matches with the lower limit. So before I get started, I'm going to have to flip this integral. So the derivative with respect to x, and when I flip the limits, I get a negative. So negative integral from 12 to x of cosecant t cubed dt. Now I guess I should point out something here I didn't point out in the last slide. It might have been good to. I have x's and I have t's. The reason that I have to change variables is this x is behaving as the upper limit. T is some variable that goes from 12 to x. I can't have x go from 12 to x because x can't go to x. X is x. So I need to have a different variable in my integrand than I have in my limit for it to make sense. I know that the derivative of a constant times something, I can bring that constant out, so that's the negative derivative with respect to x of the integral from 12 to x of cosecant t cubed dt. And now I notice that what I'm deriving over and the upper limit match, so I can just bring this negative down and I get the cosecant of x cubed. Now a question you might have is, what if the limits and the variable don't match? And the answer to that is basically you make them match with chain rule. And so here's an example. I have the derivative with respect to alpha of the integral from 3 to 2 alpha cubed of beta sine beta squared d beta. And I can see that the variable I'm deriving over and the upper limit are not the same, but this is a function in terms of alpha. And so what I'm going to do is this. I'm going to put a step here. I don't actually show this step once I start doing these, but I really want to have the derivative with respect to 2 alpha cubed, because that way these match up. So let me write down the rest. Beta sine beta squared d beta. But I can't just magically say, poof, alpha is now 2 alpha cubed. So what I need to do is somehow account for that change. And how I do that is by multiplying by the derivative of 2 alpha cubed with respect to alpha. Now, if these were behaving exactly like regular fractions, you could see that the d2 alpha cubed in the denominator and the numerator here would cancel, and I'd be left with the d over d alpha, so it'd be the same thing. Chain rule isn't exactly that, but it's close enough that it's a good explanation for what's happening. It's sort of counteracting changing this by multiplying by that. And now what I actually do is this. I see that these match now, so I would get this into every beta, and so I'd have 2 alpha cubed sine of 2 alpha cubed squared, and I had to multiply this by the derivative of 2 alpha cubed, which is 6 alpha squared. And then I just sort of wrap this up. So 2 times 6 gives me 12. Alpha cubed times alpha squared is alpha to the 5th times the sine. 2 alpha cubed squared, 2 times 2 is 4. Alpha cubed squared is alpha to the 6th. Now, we've seen what happens if the varying part is on the bottom. We've seen what happens if the limit doesn't exactly match what we're deriving over, but is a function of it. But what happens if both limits are functions of this? Well, here's how I deal with it. So I'm going to put a little space here. I'll fill this in with why it works this way shortly, but what I do is this. I first deal with the top, and I'm not going to show that step immediately, but I put this into the function. So I have tangent squared r, again, tangent r all squared is tangent squared r, minus sine of the tangent of r. And then I need to multiply this all by the derivative of that using chain rule, which is secant squared r. And then, since this is at the bottom, let me switch colors, I'm going to have a minus. Because if I flipped it up to the top, it would change the signs of things. And then I put this into both of them. So I have the natural log of r squared minus the sine of the natural log of r. And then I need to multiply by the derivative of natural log, which is 1 over r. And I'm going to clean this up a little bit. So let's see, how do I clean this up? I'll move this secant squared. I guess I'll distribute the secant squared. So I have tangent squared r secant squared r minus sine of tangent of r times secant squared r. And then I can distribute through the negative and the 1 over r to get minus the natural log of r squared over r plus the sine of the natural log of r over r. And that's the final answer. Now, going back a second, you might wonder, okay, why does this work out? And here's why. So what I'm going to do is I'm going to split up this integral, dealing one with the top limit, one with the lower limit. So I'm going to find the derivative with respect to tangent of r of the integral from some constant to the tangent of r of t squared minus sine t dt. And then, to take care of this, I'm going to subtract by, oh, I forgot something, sorry, chain rule. So I multiply this by the derivative of tangent r dr. And now, since this was at the bottom, I need to flip it up to the top for the rule to work. I subtract by the derivative with respect to the natural log of r of the integral from that constant to natural log of r of t squared minus sine t dt. And then to take care of changing this, I have to multiply using chain rule. The derivative of the natural log of r with respect to r. And that gives me all the pieces. So this here gives me that. This gives me this. This here gives me that. And this gives me this. I hope this helped out. Feel free to comment below if you do have any questions.